if you have a word problem, it really is actually helpful because then you know what all the numbers stand for and you can figure out, hey, can I just move some numbers around here and things will still work out. So sometimes we need to do what's called transposing a matrix. And that means we're going to rewrite, hang on, let me hit the little auto hide. It'll let me. Oh, of course it won't. Let me see auto hide. Well, we'll do the best we can. You've got it in your packet. It's being ornery. Sometimes you need to transpose a matrix. Transposing, I do that every once in a while. I mentioned before, 2's for 3's. I don't know why, it's just one of those things. I'll write 2 for 3 and 3 for 2. That's transposing just means we're going to rewrite it. What we can do, if we understand where the columns and the rows came from, is just switch the rows and the columns. You know, so we still know where they came from. We have identified them and what we need them for. And sometimes we have to do that. So the new matrix is called, well, the new matrix. We've got our transpose matrix, but most of the time we're not going to write that. We're going to use that notation instead. You know, in math we try to stay away from having to write in words that aren't completely necessary. So if A originally has all of its entries as the I row and the J column, what you do is you make the J's your rows and the I's your columns if you need to. So that's what the transposing does. We've got a florist and they make 3 different cut flower arrangements for Mother's Day. A pretty standard 1, 2, and 3 going that involves roses, carnations, and lilies. Matrix A shows the number of each type of flower that they use in each arrangement. So here's the arrangements, 1, 2, and 3, and that's how many roses, carnations, and lilies that they have in there. And yeah, they'll generally do this because Mother's Day is usually a really busy day. Valentine's Day is just nuts for florists. So they'll have certain arrangements that they will have for you. Now, this little matrix over here says the florist can buy their flowers from 2 different wholesalers, which is wholesaler 1 and wholesaler 2, but wants to give all his business to one or the other. And if the flowers look the same, they're going to want to go with the cheaper one. So the cost of the 3 flower types from those 2 wholesalers is shown in matrix B. So wholesaler 1 for roses, carnations, and lilies, and wholesaler 2, roses, carnations, and lilies. Like I said, if they look exactly the same and they last about the same length of time, you want to go with the cheaper one if you're the person that's the florist. So now there's a problem. Because we know if we want the price, we're going to have to take how many we need times how much each flower is. And I kept talking about this in the video because usually the easiest way to learn how to multiply matrices is just by using your fingers and saying, I need this times this, this, and this. And you just move them along that way, and your eyes eventually get used to the right and left and up and down movement and multiplying. But here's the problem. Roses times the cost of roses. Roses times the cost of carnations. Roses times the cost of lilies. Makes absolutely no sense. So, think, what if I transposed this? So what if instead of the 1, 2, and 3 up here, I put the roses, carnations, and lilies up here, and then I put the 1, 2, and 3 down this way? Would that match up? And it does. It does. So we could transpose that first matrix, and we'll just call that A. That's a T right there. And I'm going to go ahead and put the labels and everything on there. So roses, carnations, and lilies, and 1, 2, and 3. And all we do is take the rows and make them columns. So instead of row 587, this will be the column 587. Row 667 becomes the column for carnations, and then lilies 433. And then I'm going to bring that other matrix down just like it was. I think about my pattern for multiplication, I just want to double check. So this is wholesaler 1, roses, carnations, lilies. Perfect. Matches up exactly what we need. So all we have left is multiplication. But what I want to know beforehand is what size matrix I'm going to get when I get done. This is a 3 by 3, and this is a 3 by 2. So what's our resultant matrix going to be? 3 by 2, right. These threes match. This will give us our answer. 3 by 2. So probably want a calculator since this one has the decimal stuff in there. Hopefully that'll make it a little bit easier to do the math. But for arrangement 1, we're going to need 5 roses, 6 carnations, and 4 lilies. So 5 times $1.50 plus 6 times 95 cents plus 4 times $1.30. So $18.40. I think, well, what did I just find here? Well, this was arrangement 1, wholesaler 1. Next one would be, I would probably just go down to the 863 and continue on with wholesaler 1. So 8 times $1.50 plus 6 times 95 cents plus 3 times $1.30. 21.60. And you start to get the feel, hey, this is all going to be wholesaler 1 in this column. And this is going to be that first design, second design, and third design cost. Because that's what I'm multiplying here. 7 times $1.50 plus 7 times 95 cents plus 3 times $1.30. 21.05. So all of that is the cost of the flowers that you would need from wholesaler 1. So why don't you go ahead and get me column 2, and we'll check and make sure that everybody's finding those okay. Just take a couple minutes. Those that were working on this, you're doing a super job. I saw 1815 for the top entry there, which would be our first row and our second column, and then 2085. But a lot of people were just finishing up that last one. So what the last one come up to be? Feels confident? 2050. Who agrees with this statement? Matrices are not hard, but you have to stay organized. Absolutely. Absolutely. They're not difficult, but boy, if you lose track of where you're at, you are in trouble. So one of the things that I did on the video yesterday was things like this. Help people keep organized as you go through it. So if you didn't get those answers, it wasn't because you didn't know what to do. It's because you lost track of something along the way. So whatever you have to do, whether or not it's writing on your matrices or like I said, using your fingers and saying this times this, this times this, this times this, it trains your brain to go the direction you need for matrices. So this one says identity matrices, inverses. Sounds a lot like all the properties that we have for numbers. So the n by n matrix, I sub n with ones on the main diagonal. This is called the main diagonal right here, and this is the secondary diagonal. So ones all across that main diagonal and zeros everywhere else. That is the identity matrix of order n by n, n by n. So we use square matrices whenever we're talking about these. And what this does is if you take a matrix and you multiply it by this matrix, you get your original matrix back. It's like it doesn't do anything to it. It's like multiplying by 1 when we just talked about numbers. 3 times 1 is 3. So the identity matrix works that way, but we do only use this generally with square matrices. So identity matrix for a 2 by 2, 3 by 3, 4 by 4, ones on the main diagonal, zeros everywhere else. Now, at first you think, why on earth would we even study that? Could that be that helpful? When we get into solving, it is a truly big deal that we have that. So this says, if A is entries with the I row and the J column is any n by n matrix, there's the big deal right there. We're only going to be able to do this with square matrices. We can prove that if you take a matrix times our I sub n matrix, our identity matrix, you'll get the same thing as if you multiplied it from the left side, and both times you will get A. Now, here's the deal. We already know that multiplication with matrices is not commutative. A times B does not necessarily equal B times A. So whenever we want to check on something, we always have to do it both ways because it could be a different answer. So in this case, they're telling us, just checking this, that's not enough. This was multiplying by the identity matrix on the right-hand side. This is the left-hand side, and that's different. It gives you a different result for a lot of math. Shouldn't if it's the identity matrix, but it should give us A. So that is, I of n must be a square matrix is the multiplicative identity for the set of n by n matrices. So like I said, it's one of those things that to start off with seems like, why on earth are we looking at this? But for solving, it's huge when you get that identity matrix. So if A is a non-zero real number, the inverse of A for multiplicative inverses is 1 over A, and that's because if you have A and you multiply it by 1 over A, you get back to 1. The definition of the multiplicative inverse of a square matrix, similar, not exactly the same, but similar. And this says for our inverse, where we have A and B as square matrices, so we move from identity into inverse, basically how do you undo it? If we have A, which has I rows and J columns for its entries, and it's a square matrix, maybe there's some matrix B that if you multiply it on the right-hand side and multiply it on the left-hand side, you can get our identity matrix. You can get ones on the main diagonal and zeros everywhere else. If that's the case, then it has an inverse, and what you found was the inverse, because when you multiplied it, you got the identity matrix. So B equals A inverse is what we're looking at. So this one says, let's just do some verifying, all right? Verify an inverse matrix. There's A, and it says prove this is its inverse, right over here. Well, if it is, when we multiply it, we should get the identity matrix. So that's what we'll do. We'll have to do AB. And see what we get. But that won't be enough. Because remember, matrix multiplication is not commutative. So we can't just do AB, we're also going to have to do BA. And again, what we're checking here is, when we multiply by these, do we get the identity matrix? What's supposed to happen if this is truly an inverse? So let's see. 3 times 1 is 3. Negative 2 times 1 is negative 2. 3 plus negative 2 is 1. It's a good start. Just a start, but it's a good start. And now, as I mentioned on the video, you need to come up with a way to multiply these consistently, so you're always doing it the same way. So some people will always go from row 1 down to row 2 and back to column 1. Some people will say, I'm going to do row 1, row 1, column 2, and get this one. Whichever way you do it is fine, just be consistent, because then you'll constantly train your brain about which way you want to do it. I'm going to go ahead and do this position next, 6 and -6, 0, because that was row 1 and column 2. This next space here, this is row 2 and column 1. -1 plus 1. Looking good if we get a 0 in that last spot. So far, so good. -2, +3. But that means it's working in one direction. It has to work in the other direction as well. So we're going to do the multiplication again, and this would give us 3 and -2, which is 1, -2 and 2, which is 0, 3, -3, 0, -2 and 3, 1. Is B an inverse matrix of A? Yes. And it's important for us to acknowledge the reason why is that both of these showed up to be that doesn't even, Smartboard's not keeping up with me when I'm writing here. Identity. There we go. Write a little smaller. We got the identity matrix, whether or not we did A, B, or B. That means that it is an inverse. So I know it says prove, and you're thinking, shouldn't it just say verify? Basically, it's the same thing when we're talking about matrices. If we can show that we get that identity matrix, we've got it. But notice so far, we've been talking just about square matrices. And square matrices do a lot of things that non-square matrices don't. Now, determinant of a square matrix is a really important number that's associated with a matrix. And it says there's a simple test that determines whether or not a square matrix will even have an inverse. And that is the determinant. So if we can find the determinant and the determinant is not 0, then it has an inverse. And here's why. Because if we need the inverse of a matrix, we need 1 over AD minus BC. Now visually, here's what that is. It's the main diagonal and then the secondary diagonal. So main diagonal minus the secondary diagonal. And if this comes out to be 0, we're done. There can't possibly be an inverse because we'd be divided by 0 in this spot. Now that's the first step to getting an inverse. The second step is, once you have this scalar that you're going to multiply by, you have to switch and negate. So main diagonal, you swap these two numbers, D to A to D, and then you negate the secondary diagonal, -B and -C. So that will find an inverse for us. That's really important because remember, inverses are how we undo things. We want to know, how do you undo matrix multiplication? That's an inverse that we need. So, like it says here, the number AD minus BC is called the determinant of a 2 by 2 matrix. And again, we don't like writing out words, so every once in a while you'll see it written as DET of A, but this is really the way that notation-wise we let people know we're finding the determinant. That's why in the video I said it's so important that you square off your brackets for matrices, because if you don't square them off, people are going to think you want the determinant, because that's the symbolism that we use for that. And that's always going to be our little AD minus BC. So that is that determinant of that matrix. If the determinant of a matrix is 0, you can't have an inverse, because the formula for the inverse is 1 over the determinant. And if the determinant is 0, we're divided by 0. So we can't do that. Now there is some fancy language for that too. If the matrix does not have an inverse, it's called singular. If it does have an inverse, that's a good thing, and it's called non-singular. There's more math we can do with matrices that have inverses. So inverses of n by n matrices, and n by n matrix has an inverse if and only if its determinant is not 0. Yeah, they're driving that home. That's like the third time that we've seen that. So example 7 says we're going to show a matrix doesn't have an inverse. Prove that matrix A is singular and has no inverse. Well, if that's the case, its determinant is 0. So what we're really going to find is the determinant. And no, don't square that one off, because remember that means determinant there. We're going to find the determinant of this matrix. And determinants are found by main diagonal minus secondary diagonal. So this would be 6 minus 6. Now, this was showing a matrix has no inverse. Now here, it says prove. So that's not enough if we want to prove this, because when you prove something, what you're doing is you're using things you know from the past to show that something's going to work or not work. So here's what we're really trying to do. We're trying to take our little matrix times some other matrix and get 1, 0, 0, 1. That they told us that's what's supposed to happen if you have an inverse. The problem is, I don't know what those things should be, all those entries in that second matrix. Well, for the time being, since we don't know what they are, let's just use x, y, z, w. And let's set up a system of equations here and see what happens. So if we were to multiply this out, this would say 6x plus 3z has to equal 1. So we have our first equation just using matrix multiplication. This one would say 6y plus 3w equals 0. If it works. Next one, using row 2, would say 2x plus z equals 0. And then row 2 and column 2 would say 2y plus w equals 1. Now, here's the good thing. I know this isn't supposed to work because we already did this and this came out to 0. So all I have to do is show that somehow this is going to lead me to saying this doesn't have any solutions, and I'll be done. I'm going to go ahead and use a little substitution here and say, hey, I'll just move one of these over, z equals negative 2x. And now I'm going to put that into one of the other equations that uses z and hope that I can see, hey, this isn't going to work. Here's the other one that uses z. So this would say 6x plus 3 times negative 2x has to come out to 1. You see the problem? We're going to have 6x minus 6x equals 1. 6x minus 6x doesn't equal 1. 0 doesn't equal 1. So to us, that tells us this is not going to have any solutions. That's the proof. The proof is, hey, we're just using some basic algebra that we've done in the past. We solved systems in 7-1. It's not going to work. There is no solution. It isn't going to happen. Now, if it just says show, we can do this. If it says find if the inverse exists, we can do the determinant. So down here it says for each matrix, state if an inverse exists. Do we need to do a formal proof for each one of these? No, we could just do the determinant. So let's see what we get for determinants and whether or not we believe they're going to have inverses then. So we're really finding the determinant. That little bugger right there. Multiply the main diagonal. Multiply the secondary diagonal. Subtract. Negative 2 minus a negative 6 will be negative 2 plus 6, which will be 4. Does this have an inverse? It does. It's not a 0. has an inverse. It's just 0 that's a problem. All right, so for B, looks a little strange. Got a pattern going there. So let's see, 18 minus 18. Yes or no? No. Determinant is 0. Can't find the inverse. Oh, this one seems to have a whole lot of zeros. Is it good for inverses if there's a lot of zeros? Bad for inverses if there's a lot of zeros. So that's a no. Go ahead and find the determinant for D and tell me whether or not it has an inverse or not. What'd you get for the determinant? -21. Makes me a little nervous. Did the definition say anything about negatives? Not a doggone thing. This will have an inverse. It's just 0. That's a problem. Just 0. Nothing else. Determinant is 0. You will not have an inverse. Is it going to happen? Ooh, look at this one. That looks tougher. Find the determinant of a 3x3 matrix. Oh, with a calculator. Back in my day, when dinosaur roamed the earth, we had to do these by hand. And you know what? We learned to love 2x2s and 3x3s, but anything bigger than that, and things just got way out of hand. So over the years, they've said, well, it's all right if you use a calculator for some of this stuff. So we're going to take advantage of that. We just have to know where to put it in. So I better grab my packet and get over here. My calculator, so I can see the numbers while we're doing this. We have to know where matrices are on the calculator first. So why don't you take a look and see if you can find matrix. It's obviously a secondary function on your calculator, or it would have been something that people would have raised their hand right away and said, it's right here. Did you find it? Okay. Yeah, right here. Right over that inverse button there. Matrix. So let's hit second and matrix. We can name our matrices. That's helpful. Most of the time, what we're going to need these for is when we actually want to do math with the matrices. Speaking of math, what's under there? Oh, look at that. There's the determinant right there. And if you were too lazy to transpose your own matrix, which would really be lazy, you could use this, number 2, for that. And there's a whole bunch of things that we're going to get to in the future here, but this is if you want the calculator to do something for you. We're going to want it to do the determinant, but we got to put the numbers in first, obviously, and that's edit. And we might as well pick matrix A. Now notice, really important whenever you work with matrices is the order of the matrix. It's the first thing it asks you for. It's like, what size are we talking about here? So what size is the matrix we want to put in there? 3x3. 3, enter, 3, enter. And you'll see there's nice little spots for you to put them. So go ahead and put them in there. Ooh, Luke and Logan talking back there just got me thinking. Do we have inspires in here? Is everybody finding what they need for their inspires? Did you find it, Kenzie? Okay. All right, you have them in there? This is the storage spot for the calculator. It's storing all of this so that if we want to do some math with it, it'll do it. But all the math has to be done on the main screen. So once we get this in there, we're going to need to do second quit. And then on the main screen, tell it, hey, do this for us. Well, that was the determinant that we wanted. So we're going to have to hit second inverse to get to matrices, and then arrow to the right once for math, and we want them to do number 1. But we have to tell it which matrix to do that to. I know we only have one in there right now, so it seems kind of silly, but we need to tell it we want it to do matrix A, and that's where the names come in handy. So now if we hit second matrix names, we want number 1. That's the matrix we put in there. And I will finish off the parentheses. You wouldn't have to, but it looks much nicer if you finish those off there. And enter. And there's the determinant. We didn't have to do anything, which kind of bothers me. Do you want to know how to do the determinant by hand for a 3x3? No? All right, maybe I'll do that after I get done with the rest of the lesson, huh? Because there are certain things that we want to be able to do. Now, on the test, there's going to be, the first portion of the test will be a non-calculator portion. So you will be doing adding, subtracting, multiplying matrices without a graphing calculator. You'll find a determinant without a graphing calculator. But then there will also be a calculator portion where we're going to put bigger matrices on there, and those will be the ones that we use for these.
Will we have to find a determinant of a 3x3 by hand?
No, 2x2s for the determinant as far as we go. All right, let me get this big lug out of the way. Get back to the lesson. All right, so what do we get? Negative 24? There's the determinant, and that does tell us this has an inverse. But that's another thing we probably would just use the calculator for, would be to find that inverse. So example 8 says, finding inverse matrices. We're going to do the 2x2 by hand, and then we're going to grab the calculator for the 3x3. Determine whether the matrix has an inverse. If it does, find its inverse. Well, that's the determinant. We need to see what is the determinant of this little baby right here. Math in your noggin there. What is your determinant? It's a 2. 6 minus 4 is 2. So now remember, we had a formula for inverse. It's 1 over the determinant times, on the main diagonal, you have to switch the numbers. Okay, so main diagonal was 3 and 2. Now it'll be 2 and 3. And on the secondary diagonal, you have to negate. You have to put a negative in front of them. So now if we just multiply that scalar 1/2 times everything in the matrix, we should get our inverse matrix. And yeah, fractions are part of life even with matrices. It's just how it works. All right, so I'll get back to my computer over there because we have to put in our new matrix. So second matrix, and I'm going to go right to edit, and I think I'm just going to overwrite what I already had in for matrix A, which was a 3x3. And I'm sure you already have it in there. All right, first things first, we should find the determinant and make sure it's not 0. So we'll go second quit, back to the main screen, second matrix, math, number 1, and then recall the name, second matrix, number 1. So our determinant is negative 10. Does it have an inverse or not? Sure does. So now we want to find it. So inverses, how does a person find an inverse? Well, look at the button we've been pushing all this time for matrices. That is the inverse button. So let's try calling up matrix A by name and then telling the calculator, do that for us. Give us the inverse. There it is. Now, if we don't want fractions, because remember, if something doesn't come with fraction, or if we don't want decimals, if something doesn't come with decimals, we're not supposed to do that. We could even be super lazy and hit math, number 1, enter. And it'll change it all to fractions for us, so we don't have to do anything to get that inverse. Now, I'm not encouraging laziness, but and we write V inverse, and we had 1/10. Half, 0, half, and -1, 0, and 1. And from the sum of that, I must have gotten really short on time, huh? Okay, so I'll get you the assignment here. You will probably be able to do everything but maybe 1 or 2 problems, and we'll just finish that up on Monday. We're just going to talk about the properties. Basically, the key of the properties is knowing that matrix multiplication does not work